We are going to take one more class on membranes, because membranes are very important processes and there are different types of membranes and they have different principles of operations. So, I mentioned about quite a lot of membranes like reverse osmosis membrane, microfiltration and so on. Now, let us look at ultrafiltration. These are membranes, the pressure is generally of the order of 2 to 10 bar. We can use it for separating solutes based on their molecular sizes. So, we can use it for separating high molecular weight products like polymers, proteins, colloid materials, low molecular weight solutes. We can use it for concentrating fruit juices, for recovery of whey protein from cheese, and concentrate cell free fermentation broths containing monoclonal antibodies and so on actually. So, they are generally made up of polysulfones or other polymers, and they have microporous, okay, the pore size is smaller than the microfiltration. So, microfiltration will have largest pore, then comes the ultrafiltration. So, liquid flow through the membrane is by viscous flow through the pores, and you need to apply some pressure. These are moderate pressure. So, here the osmotic pressure is negligible because of the high molecular weight of the solutes actually. Then you have the microfiltration. These are very large pore sized, so they are almost like conventional filtration actually. So, large pores, so we can filter particulate matter. The pressure is of the order of 1 to 2 bar. Even normal filtration also pressure is say 2 to 10 bars actually. So, a disadvantage of microfiltration is fouling is a big problem because of the deposition of solids. So, solids build up happens at the upstream of it. Another disadvantage is concentrated slurry. So, you will not get very dry cake, okay, when you do this microfiltration. Now, let us look at another important membrane process, and this is called hemodialysis. This is an artificial kidney, especially patients who have problem with kidney, that means kidney failure. The kidney is not able to do its job of separating the salts present in the blood into the aqueous urine. Then such patients have to undergo this type of hemodialysis, okay, or it is called dialysis. Sometimes they may have to come to the hospital once every fortnight and get this done. So, what do you have here? We have a fibrous membrane here, we have the blood from the artery goes and then it goes back to the vein actually. So, blood is drawn from the artery through these fibrous membrane. Okay. On the other side we have something called dialysate. Okay. So, that liquid flows on the other side and the used dialysate is collected. So, the salts from the blood, because the kidney is not able to remove the salts effectively, the salts from the blood because of the concentration gradient flows out, goes into the dialysate which is collected and taken out actually. So, the blood is free of these salts. So, this principle is based on concentration gradient. Okay. So, we have the dialysate that is flowing outside these fibrous long tubes and we have the blood flowing inside. Sometimes the dialysate may go into the blood stream as well, that sort of possibilities are there actually. So, this is called a hemodialysis. So, it is generally used in medical field as I said. So, the blood is drawn from the patient and passed through the hollow fiber unit, the lumen it is called. Water containing solutes such as potassium salts are passed to the shell side, that is called dialysate. Now, you use salts because you want to make the osmotic pressure same as what is there in the blood as well as in the water side. So, urea, uric acid, creatinine, phosphates, chlorides, that are all present in the blood and which the kidney is not able to remove or removed in this, and then the blood that goes back into the vein is now free of all these salts actually. So, we can use dialysis also for separating alcohol from beer also. So, separate of solutes, this is through diffusion. So, the driving force is concentration difference actually, because as you know Fick's law of first diffusion, we have the diffusion coefficient multiplied by the concentration gradient. So, the dialysis membrane has non-porous characteristic of reverse osmosis and microporous characteristic of ultrafiltration. The process is slow when compared to reverse osmosis or UF actually ultrafiltration. Okay. So, the solute flux, that is of J is equal to R, that is the membrane resistance plus film resistance on both sides, you will have both sides into delta C. Delta C is the concentration gradient. So, if you have say a porous membrane in the middle, okay. So, you have the blood flowing like this and the dialysate flowing counter current, the solutes, okay, diffuse out into the tube side of the dialysate. Okay. Now, you can have films here on both sides, you can have a film resistance inside on the blood side as well as the film resistance on the dialysate side, both are possible. So, they all contribute to the R, that is the constant, that is the membrane resistance plus these film resistances on both sides. So, delta C is the driving force. Generally it takes hours, especially if a patient is undergoing dialysis. So, the dialysis clearance, that is Kd it is called, ml per minute, determines the removal rate of a substance from the blood. So, it depends on characteristics of the dialyser, nature of treatment method and so on. So, we can do a mass balance here, Kd into Ci, okay. Ci is the concentration of solute in and C naught is the concentration out. Ci is the concentration of the solute coming in, C naught is the concentration going out, and Qi and Q naught are the blood flow at the inlet and the outlet. Okay. The difference is what is getting transferred, that is Kd into Ci. So, C naught is what is going out is much smaller than Ci, and generally Qi and Q naught are almost same actually, that is the total amount of blood flow. We assume that the blood does not diffuse out into the dialysate side of it. Okay. So, what we can do is, if Qf is the ultrafiltration rate, that is some blood flow also escapes through the membrane, then Qi is equal to Q naught plus Qf. But if no blood or fluid escapes, Qi is equal to Q naught, which is equal to Qb. So, we can have Kd is equal to Qb into 1 minus C naught by Ci. Okay. So, if you assume there is some blood that is escaping, okay, then we will have slightly complicated equation, but if we assume that there is no blood escaping into the dialysate, whatever blood coming in, whatever blood go out is equal to blood same, okay, Qb blood flow. Okay. So, Kd is equal to Qb into 1 minus C naught by Ci, okay, where Kd is this dialyser clearance, okay, ml per minute. Okay. C naught is the concentration of the solute going out of the dialysis unit, Ci is the concentration of the solute entering the dialysis unit, okay, and that is called the clearance. There is another system that is called electrodialysis. So, as the name implies, we apply an electric field so that the salts, that is ions, cations and anions, move to the electrodes. Okay. So, what happens here is we have compartments, these are all called compartments and they are all separated by membrane. So, you have a anion permissible membrane, you have a cation permissible membrane, anion permissible membrane, cation and so on actually. Okay. So, you have say protein with salt that is entered and then you are applying a voltage here, cathode minus voltage, here anode plus. So, what happens? All the cations will try to move there, okay, all the cations will try to move there actually, okay, and the anions will go the other side actually. Okay. So, you will end up having pure salt collected in alternate compartments and okay, and purified protein collected in the other alternate compartments. So, when we have a positive and negative the cation and the anion for the salt, so pluses will try to go there, minuses will go there, pluses cannot go there because it does not allow, it is an anion permissible membrane. So, what will happen is there will be a concentration, okay, of the salts in the alternate membranes and there will be concentration of protein which are devoid of the salts in the alternate. So, we can collect the purified protein and we can collect the salt solution in the alternate compartments, or if we want to desalinate water by using this type of electrodialysis unit, we can get pure water from alternate set of compartments and saltish or brackish water on the other set of compartments. So, this can also be used for desalination of water, especially if you have a electrical power generating system there, then this type of electrodialysis is very good instead of going for RO. RO, if you are closer to a sea and you need to apply very high pressures, whereas if you are closer inland and if you are closer to a electrical power generating unit, then electrodialysis may be a better system actually. So, both have advantages, disadvantages, and you can select based on the conditions and what are the requirements actually. So, electrodialysis can also be used for removing salt from protein solutions, for desalinating salt water and so on actually. So, the electrodialysis, desalination of brackish water, separation of ions due to the potential difference across the ion selective, cationic and anionic exchange membranes. The driving force is the applied electric field which induces a current, that is the ionic flux. So, what is the mathematical relation? I, the current, is equal to F, that is the Faraday constant, N is the solution normality, Q is the flow rate, eta is the removal efficiency divided by N is the number of cells, E is the current efficiency. Okay. So, the current can be calculated using the Faraday constant, solution normality, the flow rate, number of cells and current efficiency. So, the electrodialysis power is given by power is equal to I square R. Okay. So, if the resistance is very high, power also will be very high, power requirement. The next membrane based technique is PERV operation. So, this uses a membrane, uses a PERV operation membrane. It is a combination of permeation and evaporation, that is why it is called PERV operation. So, the solution is initially evaporated by applying some heat as well as by applying a high vacuum, and then the solute molecules permeates or diffuses through the membrane material because there is an affinity for the solute to the membrane material. So, it diffuses it and it goes to the other side where it is again becoming a liquid, and that way it is collected actually. So, separation of two or more components is achieved with the help of a thin non-porous polymer. So, you have to remember this, in PERV operation the material is not porous, unlike your microfiltration or ultrafiltration where the material is porous. So, depending upon the rates of diffusion of the solutes through the membrane material, the separation can be achieved. Okay. So, evaporation of the solution is achieved by little bit heating and applying a vacuum. This is a typical PERV operation setup. So, what you have is feed solution, you are applying some heat here, at the same time you are applying vacuum on the other side. So, the vapor comes here, it settles on the membrane material, PERV operation membrane material, diffuses through, on other side it is condensed using a condenser and the liquid is condensed and taken out actually. So, you apply a vacuum on one side and heating on the side. So, there are no pores in the membrane material. So, your solute travels through the membrane because of diffusion and it is condensed here on the condenser side. So, what are the advantages? It requires low temperature and pressure. So, if there is any thermally labile products like fruit juices or syrups, sugar solutions, or then it is easy to operate. It is lower cost and better performance than using say azeotropic distillation. It is economical for dehydrating organic solvents. Suppose I want to make 100% butanol, that means I want to remove all the water. If I want to make 100% ethanol, then I may have to resort to azeotrope, I may have to add some third component to break the azeotrope. So, whereas PERV operation does not require that. So, we can remove organics from aqueous streams, there is no entrainment required. So, there is no contamination, especially in azeotropic distillation we have to add a third component which could be a contamination. It is independent of vapor liquid equilibrium. So, it does not depend on vapor liquid equilibrium like distillation, okay, it just depends upon the diffusion of solutes through the membrane material. So, it can be performed in batch or continuous. It is suited for separating heat sensitive material, food products, pharmaceutical products and so on. So, the liquid movement is explained based on solution diffusion. We can achieve higher flux, increased thermal motion of the polymer chains by diffusion. So, the properties of the polymer affect the diffusion process, the backbone material, degree of cross linking, porosity, all these will affect. It is a molecular level interaction because the solute molecule diffuses through the polymeric material actually, that is what is happening. So, it is generally mentioned expressed in the term of Arrhenius equation. So, pervaporation is accompanied by change of phase, you need to remember, because you are heating, so you are forming vapor, then solute goes through, on the other side solute is condensed, it becomes liquid. So, it is much more useful than azeotropic. Sometimes you can use carrier gas also, so that we can drive this. So, the separation is not based on vapor liquid, but it is based on solubility and diffusion of the species through the membrane. Okay. So, it is based on solubility and diffusion, whereas distillation is based on vapor liquid equilibrium. So, this is a good book, Journal of Membrane Science, if you want to know more about polymeric membrane related to pervaporation. Okay. Now, pervaporation, as I said, you have a liquid and feed mixture, there is in thermodynamic equilibrium with the membrane mixture actually. So, we have K, the partition coefficient will be equal to Cm by C feed. Cm is the concentration of the species on the membrane surface, C feed is the concentration of the species in the feed solution. So, that gives you the partition coefficient. Okay. So, by selecting suitable membranes we can achieve very high partition coefficients, and then membrane transport, that is transport of the solute through the membrane, is by Fick's law of diffusion. Okay. So, Fick's law is N permeability flux is equal to minus D diffusion coefficient multiplied by dC by dx. So, or if we differentiate it, we end up with N equal to capital D is diffusion coefficient, K is the permeability, delta is the membrane thickness, delta C is your driving force. So, that determines your flux on the left hand side, correct. Then the permeability is generally expressed like an Arrhenius type, P0 E minus EP by RT, EP is the activation energy, okay. R is the gas constant, T is the temperature, this P gives you permeability, this is a permeability constant. So, the molecular flux J is given by Q by AT, A is your area, membrane surface area, T is your time, obvious, right, J is your flux, that is component permeated per unit time, that is why it is called flux. So, we have put I, similarly we can have J, we can have K, different species. So, for each of the species you can have different flux, molecular flux here actually. What is perm selectivity? That means selectivity for one particular species. If we have I, J, K, L and so on, the selectivity will be equal to Vi P, Vj P, okay, for the species P, and F denotes permeate and feed, okay. So, we have I species I, J species J, then I species I, J species C. So, this is P is permeate and F is your feed, okay. So, this tells you what is the perm selectivity, that means what is the selectivity for species I with respect to species C, that is what this particular equation tells you actually, correct. And P determines permeate, F is your feed. So, for given a feed Vi, the permeate is VIP, for given a feed Vj, permeate is Vj. So, that ratio is what is called alpha, perm selectivity. So, what are the industrial applications? Like I said, we can do lot of things with pervaporation, wastewater contaminated with organics, I want to remove only the organics, pollution control, recovery of organic compounds from the process side. We can make very pure ethanol because ethanol in water form azeotrope, after certain concentration we may have to add a third component if we want to completely remove one of the species, okay. That is if I want to completely remove water, but whereas with pervaporation we can get even almost 100% ethanol. So, we do not need to add another component. Harvesting of organic substances from fermented broth. So, pervaporation is very good. So, two types of pervaporation, we can have batch, we can have continuous. So, batch is simple, highly flexible, so it just needs a buffer tank. Continuous is consumes very little energy, is very good for low impurities, large capacities, this is very good. Vapor phase permeation is preferred for feeds from distillation columns or free from feeds from dissolved solids. So, hydrophilic membranes are used to remove water, right. So, because hydrophilic membranes will like water, So, generally we use hydrophilic membranes. Polymers with glass transition temperature above room temperature like polyvinyl alcohol. Organophilic membranes are used to recover organics, obvious, right. If it is an organic, so you like organophilic membrane like elastomeric materials, polymers with glass transition temperatures below room temperature. Nitrile rubber, butadiene rubber, styrene butadiene rubber. So, if I have to remove water, I use hydrophilic membranes like polyvinyl alcohol. If I want to recover organics from a mixture, I use organophilic membranes like nitrile butadiene rubber, styrene butadiene rubber and so on. Okay. So, generally they have glass transition temperature below room temperature, whereas hydrophilic membranes will have glass transition temperature above room temperature. So, that is how you select membranes depending upon what you want to remove. So, typically we can connect pervaporation and distillation like this, okay, so that we do not need to have azeotrope breaking at all. Suppose there are azeotropic mixtures which you want to break, we can just add a pervaporation system to that. So, if you have a lighter solvent, what we do is we do the feed and then here you are collecting the heavy like water. Now, the solvent goes up, so we can use a pervaporation system, then collect all the solvent and then remaining is passed in. If it is a heavier solvent, okay, so here water goes down from the top and the solvent is collected here and the product goes out like this. Okay. So, we can have different types of systems, okay, different types of systems for heavy as well as for lighter solvents, and by combining a distillation column with the pervaporation system, we can easily break azeotropes whether the solvent is light, or we can easily break azeotropes if the solvent is heavy. Okay. Then comes isoelectric focusing. Here also membranes are used for isoelectric focusing based concentration of proteins. What is isoelectric focusing? What is isoelectric point? This is the value of the pH at which the charge on the molecule is 0. So, if you have a protein, protein generally will have charge because of presence of polar groups, non-polar groups and so on. So, at a particular pH the charge will be 0, that is called the isoelectric pH. Okay. Generally isoelectric separation happens in a 2-dimensional electrophoresis. The first part is isoelectric pH, the second part could be molecular weight based and so on. So, if I pass proteins in a pH gradient, okay, at a point where the charge becomes 0, when they balance, the protein will stop moving, okay, and that is how you do separations in isoelectric focusing type of system. Suppose I have a feed passed at a pH of 6, I have 3 proteins A, B, C. Okay. Now, protein A has isoelectric pH of 7, protein B has isoelectric pH of 6, protein C has isoelectric pH of 5. So, what happens? Protein B will not have any charge because the pH and matches with the isoelectric pH of B. So, when it is fed here, you are applying a voltage, okay, you have an anode here, you have a cathode here, okay, when you are applying a voltage, now this zone has a pH of 5, this zone has a pH of 7 and you are applying a positive charge and a negative charge. So, what will happen? Protein C will try to move to this compartment, and once it moves the charge gets neutralized because isoelectric pH matches with the pH of 5. Same thing happens, protein A will move here, and once it moves here the isoelectric pH matches with the pH 7. Okay. So, the protein A gets separated in the compartment with pH 7, protein B will pass through, which is because this is pH 6, protein C will have compartment where pH is 5. So, this is how you separate. This type of system is good if the isoelectric pHs are quite distinct from each other, okay, but still you can have little bit of mixing in the final compartments because you have the anode and the electrodes coming here. So, the last compartment generally are not very accurate or exact. So, these are some of the disadvantages. For example, if you take a gelatin of molecular weight, this is the isoelectric pH 4.885. In insulin 5.3 to 5.3, cytochrome C 9.7, myoglobin 7, urease 5 to 5.1, hemoglobin 6.9. So, you see they are quite distinct in their isoelectric pH. So, separations are possible here. So, what are the problems? Continual remixing of purified materials with semi purified, that can happen. Heat is generated during the process, because when there is a mixing and then the pH changes, a lot of heat is generated. So, the setup needs to be cooled. So, these are the big problem. So, purification, simultaneously you are getting a crude which is semi purified, that is a problem. Other one is Joule heat, because of the heat, because of the mixing, heat is generated, that is called Joule heat, which needs to be dissipated. So, you need to have some cooling system to get rid of the heat that is generated. Okay. Then comes membrane bioreactors. Nowadays bioreactors are coupled with membrane, so that we can achieve a combination of filtration and reaction together. So, membrane bioreactors are becoming very fashionable. So, we have two types, where reactor and the membrane system are separate. Okay. So, after the reaction, the product comes out and there is a separation taking place, permeate comes down, like your metabolite for example. Membrane retains the biomass and other large molecules, which are again put back into the reactor. So, continuously, for example, I want to remove butanol. As you know, butanol, butyric acid, the organism can get it's deactivated because of presence of butyric acid. So, if I have a continuously removed the butyric acid here, the organism will be still alive, so it can go back. Same thing with ethanol production. Many of the yeast are stable only up to 15% ethanol. If I continuously remove ethanol here and then put back my organism, they will be active for a very long time. So, that is one type. Other system is internally you have the membrane. Okay. So, continuously as the product is formed, the permeate gets removed, and so the retentate will contain your biomass, salts and other large molecules all the time getting fermented here. Okay. So, the retentate can be collected from the top. So, that is a membrane bioreactor, where the membrane is located inside the reactor. This is another membrane bioreactor, where the membrane system acts as a filtration located outside the reactor, and the products are recycled back, that is the retentate are recycled back. So, two different approaches by which membranes can be used in combination with bioreactors. So, systems may consist traditional stir tank reactor with the membrane separation unit. Membrane acts as a support for the catalyst. So, sometimes catalyst can be impregnated or supported on the membrane. Okay. For example, catalyst can be flushed along with the membrane, segregated within a membrane. Inside the membrane, catalyst can be segregated. It can be immobilized in or on the membrane by entrapment, gelification, physical adsorption, ionic bonding, covalent. So, the catalyst remains on the membrane, product or the metabolites can be filtered out and collected on the other side, that is the filtrate. So, the retentate can be on the upstream side all the time. So, this is very advantageous system, increases reactor stability, productivity, improved product purity, quality, reduction of waste. You do not even need a separate filtration unit. So, your catalyst is kept very effective or very active for a very long time. So, they have been used in large number of systems, synthesis of lovastatin with the Candida rugosa, production of diltiazem, chiral intermediate using multiphase extractive enzyme, synthesis of isomalto oligosaccharides using a recycled membrane bioreactor, production of a derivative of chiotrofin analgesic, okay, using a alpha aminomesophorus tubular support and alpha chymotrypsin, biodegradation of high strength phenol solutions using a Pseudomonas putida trapped in microporous hollow fiber. So, large number of systems, large number of examples are already come into market, where membrane is combined with the reaction to achieve separation or immobilization and so on actually. So, we have spent a couple of lectures on membrane systems. So, the process of for separating mixtures by using thin barriers, okay, polymeric, synthetic or non synthetic material between two immiscible fluids. So, driving force although I have said concentration, pressure, you can have voltage and so on actually. So, large number of systems, microfiltration, ultrafiltration, nanofiltration, reverse osmosis, we looked at dialysis, which is very important in medical field, electrodialysis, peroperation, isoelectric focusing, membrane bioreactor. So, large number of applications for membranes and it is growing day by day. A large number of polymeric systems, hydrophilic polymers, hydrophobic polymers are being now coming into market, but the main problems are which I talked about in the last class, things like formation of biofilms, compaction of the membrane, formation of scales, closing of the pores and so on. So, these needs to be addressed in order to further increase the use of membrane in downstream applications as well as in the bioreactor applications. Thank you very much.